One of the most remarkable characteristics of humanity is our history of advancing technology. We made tools from stone, then bronze, iron, and steel. We learned to hunt and gather, then to farm and fish. We created towns, then cities, then nations. Each of these developments brought dramatic and irreversible changes to the world. And the most exciting part is we're still advancing. Many historians refer to our current historical period as the information age. With the advent of computers, the foundation of our economy has quickly shifted from traditional industry to information technology. Communicating and accessing information has never been easier. There's a good chance that you are carrying an access point to the entirety of human knowledge in your pocket. We know that computers are important, but what are computers? At their most basic level, computers are systems that take input from a user, process it, then display the results of the computation or store the results to be used later. Let's look at each step of this process. Before a computer can work, somebody needs to physically put information into it. In computer terms, this is called input. Pressing a key on a keyboard, clicking a mouse, tapping a touch screen, pushing a button on a game controller, and speaking into a microphone are all examples of input. Each of these input devices sends electrical signals into the computer. By themselves, these signals don't mean much. However, the computer quickly performs calculations on the input, converting the raw electrical signals into data. This is called processing. For example, the computer may process input from a button on a controller into a command to make a video game character jump. Once processing is done, there are two things the computer can do with the data. The first is to return information to the user, which is called output. Images on a screen, sounds from speakers, and printed pages are all output. In our video game example, the output consists of the character jumping on the monitor and a sound playing on the speakers. Once the character has jumped to a new platform, the computer writes his new location into its short-term memory. The other option for processed data is to be remembered for later use. This is called storage. When the player saves her game, the computer records information about the game into its long-term storage. This lets the player turn her game off, then pick up where she left off when she comes back. Talking about this process step by step may make it seem slow. However, modern computers can execute millions of instructions every second. Computers can do amazing things. It seems incredible that if I touch this piece of glass in just the right way, a pizza will show up at my house. Yum! However, simple or complex, all computing is based on the same 4 steps: input, processing, output, and storage.
In today's world, computers are everywhere. Just about every aspect of our society, from global communications and transportation to education, shopping, and even dating, has been influenced by computers. For many young people today, it can be hard to imagine what life must have been like before smartphones and the internet. In this video, we're going to briefly outline the history of computers from the first electronic computing machine to the present day. The first electronic computing machine was invented by Herman Hollerith to compile data for the 1890 United States Census. Hollerith's machine, which he called a tabulating machine, worked by punching census data onto paper cards. For example, if a person was female, the census taker would punch out the female spot on the card. Then they'd feed the card into the tabulating machine, which would detect which holes had been punched and record the data. Hollerith later founded the Tabulating Machine Company, which eventually became International Business Machines, or IBM. As IBM's machines grew more powerful, they also grew in size. Many early computers were big enough to fill a whole room and weighed thousands of pounds. Because early computers were large, expensive, and difficult to maintain, most computers belonged to businesses, governments, and universities. Part of the reason they were so big was that they relied on large triode vacuum tubes to relay information through the system. This changed in 1947 when scientists at Bell Laboratories invented the transistor. Transistors were able to replace the bulky vacuum tubes, which made computers smaller. Because transistors are made with silicon, and because most of the research was done in California's Santa Clara Valley, that area became known as Silicon Valley. One of the next major breakthroughs in computing was in 1959, when Jack Kilby invented the microchip. With this new technology, it became possible to have an entire computer on a single circuit board, instead of in a large and bulky machine. This made computers much smaller and cheaper to manufacture, and paved the way for personal computers in the home. In 1977, 3 successful personal computers were released: the Apple II, the TRS-80 Model 1, and the Commodore PET 2001. 4 years later, IBM followed up with the IBM PC. Since these new computers were inexpensive to buy and easy to use, personal computer ownership started to take off. Most people who owned computers during this period used them primarily as tools for work. Before the spread of PCs, almost all word processing was done on typewriters. Now, people could type and save documents on their computer. About this time, video arcades became popular, featuring titles like Pac-Man, Galaga, and Donkey Kong. Word processing was the most widely used personal computer application until the mid-90s, when the World Wide Web became available to the public. Using a device called a modem, users could dial into their internet service provider over their telephone line. Before long, the internet became a part of everyday life. People could work, shop, and communicate with friends and family at any time as long as they had access to a computer. Internet access was mostly limited to desktop and laptop computers until 2007, when Apple released their first smartphone, the iPhone. With smartphones, people could access the internet from anywhere using a device small enough to fit in their pocket. Today, almost all cell phones are smartphones. Computers and the internet have transformed society and are central to the modern world. At the rate we've been advancing, it's likely only a matter of time before today's cutting-edge technology seems as old and clunky as the first tabulating machines. Every single computing device, whether it's a desktop, notebook, tablet, or phone, is composed of 2 general components, the hardware and the software. Hardware comprises the physical components of a device. All the parts you can see, like screens, keyboards, wires, and chips, are hardware. By itself, hardware can't do very much. In order to work, it needs software, which is a set of instructions that tell the hardware what to do. Operating systems and applications are examples of software. The way the hardware and software is implemented can vary between different types of computing devices. We're going to look at 3 general categories: desktop computers, notebook computers, and mobile devices. Desktop computers have been around for years and are very widely used, especially in business and industry. Desktop computers are typically composed of the computer itself and peripheral devices, which typically include a monitor, a keyboard, a mouse, speakers, and video cameras. Desktop systems have many advantages over other types of computing devices. They're modular in nature, meaning you can combine different pieces together to customize the system to do exactly what you want it to do. They're easy to repair and upgrade, and they tend to be much more powerful than other types of computing devices. Desktop systems also have the following disadvantages. They're not mobile, and they require AC power to function. Notebook systems are much more mobile than desktop systems. Notebook systems have the following advantages. They are much lighter and more compact. They include integrated mouse and keyboard functions. They include wireless networking hardware, and they use batteries that allow them to run for a period of time without being plugged into an AC outlet. However, notebooks also have the following disadvantages. They're difficult to upgrade or repair. They're usually more expensive than comparable desktop systems, and they typically have less computing power than comparable desktops. Mobile devices, including tablets and smartphones, are very small computing devices. They have the following advantages. They're more mobile than any other type of computing device. They include a variety of integrated hardware, including cameras, microphones, and wireless networking. A wide variety of inexpensive apps are available. They can be less expensive than notebooks or desktops, and they use a touch-screen interface. Mobile devices also have the following disadvantages. They're difficult to repair and nearly impossible to upgrade. If the battery fails, it can be very difficult to replace. And they're difficult to use with productivity applications. No one type of computing device is best. The most appropriate type of computing device depends upon the situation. For a programmer or a graphic artist, a desktop system is typically the best choice because it has more computing power and can be connected to larger monitors. For a traveling salesperson, a notebook might be the best choice because it provides the basic functionality of a desktop, but is also mobile. For a telecommuting home user, a desktop or notebook system is probably the best choice because they're capable of running productivity applications they will probably be required by the user's employer. For a college student, a notebook or tablet system is probably the best choice because they're highly mobile devices. For a gamer, a desktop system is probably the best choice because it can be customized to meet the computing demands of visually intensive video games. In this lesson, we introduced you to computing devices. Two key components comprise any computing system: the hardware and the software. There are three different general types of computing devices: desktops, notebooks, and mobile devices. Each type of device has its advantages and disadvantages. Different types of systems are appropriate for different types of users.
When we think about the internet, we usually think about using a computer or phone to browse the web, shop online, or send email. However, an increasing number of everyday objects are being built with internet connectivity. The concept of connecting many kinds of devices to the internet is called the Internet of Things, or IoT. In this video, we'll look at several areas where IoT technologies are emerging. You may have heard the term smart home, which refers to a home with devices that can be controlled remotely over the internet with a phone or computer. Many smart homes have internet-enabled security systems. Indoor and outdoor security cameras record live video footage that the resident can view from their phone or tablet, and alarms inform the police in the event of a break-in. Thermostats can learn the resident's daily routines and adjust the temperature of the home accordingly. Even home appliances like refrigerators and coffee makers can be controlled over the internet by phone. Another area that is seeing an increase in smart technology is the automotive industry. Owners of internet-enabled cars can use their phones to lock and unlock their doors, monitor their gas usage, and check their engine status. Online navigation software can be used instead of GPS, and music apps can replace the need for traditional radio. In coming years, cars and trucks will use the internet to drive themselves, without needing a person behind the wheel. Driverless cars will create a massive impact on the transportation industry and change the way we think about getting around. IoT technology is widely used in emergency and medical scenarios. Smart ambulances can communicate with traffic lights, changing them to green as they approach. This green corridor lets emergency vehicles arrive at their destination faster and more safely. Patients with heart or breathing problems can wear internet-enabled sensors that automatically contact emergency services if they sense a problem. In this video, we talked about the Internet of Things. We discussed IoT applications for homes, cars, and emergency services. As technology improves, we can expect to see more IoT devices in our daily lives.
Computer technology is empowering. It gives us access to information and tools that can have a positive impact on our lives. However, technology can also be used to harm other people. This is where ethics come into play. Because computer technology expands human agency in letting us do things that we couldn't otherwise do, we need to embrace ethical principles and responsibilities in using it. Before we talk about specific ethical principles, let's look at some examples of unethical behavior that relate to technology. Example 1. A college student decides to humiliate a former friend by posting embarrassing photos on social media. Example 2. An IT specialist violates the privacy of a fellow employee by viewing her confidential personnel files. Example 3. An engineering team endangers the lives of hospital patients by releasing a software product before it's been thoroughly tested. The team is rewarded with a performance bonus for meeting their product release deadline. Example 4. A high school student hacks into her high school's academic records database and changes the grades of fellow classmates. Example 5. The IT staff at a hospital shares genetic information about specific patients with a life insurance company. In addition to being unethical, some of these actions are also illegal and can have serious consequences both for the victims and the perpetrators. But whether or not specific laws have been passed to discourage unethical actions, it's still our responsibility to treat other people with dignity and respect. Computer ethics require you to do more than simply avoid unlawful acts. They describe personal behaviors that show responsibility and trust, even when no one is watching. Here are some basic ethical principles that apply to a wide range of scenarios. The principle of confidentiality means that we protect data and information we're not authorized to share. The principle of human dignity means respecting and honoring the inherent worth and right to privacy of other people. The principle of civility means observing the rules of netiquette that promote courtesy and respect in online settings. The principle of digital property rights means recognizing and respecting the intellectual property of others, including online data, login information, creative works, and other digital assets. Information technology professionals often develop a code of ethics for themselves and their organizations. Even if you don't become an IT professional, you'll be required to make moral decisions in a variety of situations. Developing a personal code of ethics can help you identify values, principles, and rules of behavior to keep you, your family, and your colleagues safe. For example, your personal code of ethics might include statements such as this. 1. I will not violate the digital property rights of those I encounter online. 2. I will honor the privacy of others by keeping their data and information secure. 3. In communicating with others online, I will promote courtesy, respect, and understanding. Living safely and ethically in the digital world requires both knowledge and personal responsibility. As you become more familiar with the power of computer technology, you should also maintain a firm commitment to principles of ethical behavior.
When we count things, we use 10 digits, 0 through 9. This system of 10 digits is called the decimal system. However, it's not the only way to express numbers. In this video, we're going to learn about two other systems that are used by computers, binary and hexadecimal. Now, this video is going to talk about some math, but don't worry, we won't make you do any math on the test. When we count in decimal, we start at 0, then go through each digit all the way to 9. Once we hit 9, we change the 9 to a 0 and put a 1 in front to give us the number 10. This pattern continues for the tens place. Once we get to 9 tens and 9 ones, we change them both to 0 and add 1 to get 100. Binary numbers work the exact same way, but only use two digits, 1 and 0. Counting starts at 0, then goes to 1. Since 1 is the highest digit, counting continues by changing the 1 into a 0, then adding a 1 in front of it. This looks like the decimal number 10, but it's actually the binary number 2, which comes after the number 1. To continue counting, we add another 1, then change both ones to zeros and add a 1 in front. Let's look at it another way. Here's the decimal number 217. This number is made up of 2 hundreds, 1 10, and 7 ones. The ones place can be expressed as 10 to the 0 power. Tens are 10 to the first power, and hundreds are 10 to the second. This is the same number 217 written in binary. These numbers along the top represent the powers of 2, just like they represented the powers of 10 in decimal. This binary number is made of a 1, 0 2s, 0 4s, 1 8, 1 16, 0 32s, 1 64, and 1 128. If we add all these values, we get 217. At this point, you may be asking yourself, why is binary so important? Why can't a computer just use decimal like a normal person? The answer has to do with how computers work. For a computer, data exists as physical signals, such as an electric charge. Electric charge can be positive or negative. Those are the only two options. By interpreting positive charges as ones and negative charges as zeros, the computer can turn the physical signal into a number, digital data. It can then use that number to perform computations and calculations, resulting in useful information. Now let's take a look at the hexadecimal number system, which uses 16 digits. The numerals 0 through 9, and the letters A through F. Just like the other systems, counting in hex starts at 0, goes up through each digit, then resets to 0 with a 1 in front. If we keep counting up, we'll get to the hexadecimal number FF, followed by 100. By now, you're surely wondering why anyone would ever use such a silly number system. The reason has to do with how well hex translates to binary. The hex number F is equal to the binary number 1111. Adding 1 to either number will increase the number of digits in the number. This means that a single hex digit can represent 4 binary digits. Look at this binary number. It's huge. Can you imagine being a programmer and having to type this whole thing out? Let's translate it into hex. All we have to do is break it up into chunks of 4 digits, find the hex value for each chunk, and voila! A nice, easy-to-type hex number with the exact same value as the original binary. We've just taken a first look at two number systems, binary and hexadecimal. Don't worry if you feel a little overwhelmed by the math. The most important thing to know is that binary represents physical signals inside the computer, and hex is an easy way for humans to represent binary numbers.
As you know, we live in an increasingly digital world. But what exactly does digital mean? Let's take a look. Everything that happens on a computer is the result of real-world physical signals. For data traveling through a wire, the signal may be positive and negative electric charges. Many hard drives use tiny particles that can have either a north or south magnetic charge. Optical discs like CDs and DVDs are covered in microscopic light and dark spots. In every case, the two types of signals can be represented conceptually by ones and zeros. When a physical signal is interpreted by converting it into binary numbers, it's called digital data, which is the foundation of how modern computers work. Each individual signal, each one or zero, is called a bit. 8 bits together are called a byte. Each byte has 256 possible combinations of ones and zeros, from 8 zeros all the way up to 8 ones. You may have heard of 8-bit computers, graphics, or audio. These are computers that can process 8 bits or 1 byte at a time. 8-bit graphics, such as for 8-bit video games, were limited to only 256 colors, since 1 byte has 256 combinations. Today's computers generally run on 32 or 64-bit operating systems, which means they can process 4 to 8 bytes at a time. As opposed to 8-bit systems that have 256 combinations of ones and zeros, 32-bit systems have almost 4.3 billion combinations. Compare this 32-bit picture with this 8-bit picture and see the difference. One of the most important things computers do is to represent text. Let's look at a common way to encode text in binary. Here's a simple 2-word sentence, "Hello world." Each character has a unique binary code to represent it. For example, the code for this capital H is 010010000. Altogether, the sentence can be encoded like this. Remember, these ones and zeros are just stand-ins for physical signals, such as magnetic or electrical charge. But by converting the signals to binary, the computer can display the sentence. Next, let's look at how to encode integers. With 32 bits, you can represent numbers up to nearly 4.3 billion, or 32 ones in binary. However, integers can have a positive or negative value, so there has to be a way to encode that information. Computers do this by using the first bit for the sign, 1 for negative and 0 for positive. Then, the remaining 31 bits are used to encode the number itself, giving us a range from about negative 2 billion to positive 2 billion. Since bits and bytes are so small, we don't normally talk about them individually. Instead, we use the metric system to describe a lot of them together. When we talk about data storage, we usually refer to the number of bytes. 1 kilobyte of storage space is the same as 1024, or 2 to the 10th bytes. A megabyte is about a million bytes, or 1024 kilobytes. A gigabyte is about a billion bytes, or 1024 megabytes. A terabyte hard drive has 1024 gigabytes of storage space. When we talk about throughput, or data transmission from one computer to another, we usually refer to the number of individual bits that can be transmitted in 1 second. For example, a gigabit internet connection can send a billion ones and zeros every second. Note that in the abbreviations we use a lowercase b for bits and an uppercase b for bytes. Finally, let's talk about processing speed. We mentioned earlier that 64-bit processors process 8 bytes of data at a time. In other words, it can receive or send 8 bytes of data at once. Each time the processor writes data to memory or reads data from memory is called a cycle. Just like with storage and throughput, we use the metric system to describe how fast a processor can execute cycles. The base unit of measure is the hertz. 1 hertz means 1 cycle per second. A 64-bit, 2 gigahertz processor can process 8 bytes of information 2 billion times each second. That's a lot of ones and zeros. We've just learned that the word digital refers to computers interpreting physical signals as ones and zeros, called bits, and that 8 bits form a byte. We also saw how bits can be used to represent text and numbers. We ended by discussing units of measure for storage, throughput, and processing speed.
In this video, we're going to look at two schemes that computers can use to translate binary code into text: ASCII and Unicode. ASCII, or the American Standard Code for Information Interchange, was developed in 1963. ASCII was a 7-bit code, which means it could represent 128 different characters, from 7 zeros all the way up to 7 ones. Each letter and symbol was assigned a number between 0 and 127. Capital S was 83, lowercase s was 115, and the dollar sign was 36. With 128 values, there was plenty of space for the entire English alphabet, the numerals 0 through 9, and the most common punctuation marks. These 128 characters worked great for English, but weren't sufficient for writing in other languages. Fortunately, since a byte has 8 bits and ASCII only used 7, there was plenty of space to add new characters. People started adapting codes 128 through 255 to meet their own needs. In the United States, it was common to use these extended characters for additional symbols, such as accented letters and math symbols. However, other countries had other needs. In Russia, they were used to encode Cyrillic characters. Israel used them for Hebrew characters. Thailand used them for Thai characters, and so on. This system worked well enough until it became more common to transfer files between computers internationally. Resumes sent from Americans to Israel would arrive as rugzumgas because the accented E and the Hebrew letter gimel were both encoded to number 130. And that's to say nothing of languages like Chinese and Japanese, which have thousands of characters each. With the internet just around the corner, a better solution was desperately needed. In 1992, a group called the Unicode Consortium released the first version of Unicode. Unicode used 16-bit encoding and was capable of representing millions of different characters, enough space for every character from every human language, with plenty of room to spare. So much room, in fact, that developers started assigning Unicode values to pictures called emoji. With Unicode, computers around the world can access files in any language and be assured they'll display properly. We've just learned about two text encoding standards: ASCII, which was used in the early days of computers, and Unicode, which is widely used today.
In the early days of recording, sound and video had to be recorded and stored using analog methods, which means they had to physically represent the images and sound waves they wanted to record. If you've ever seen a movie played from a film reel or listened to a vinyl record, you've experienced analog recording. Today, however, most sound and video are recorded digitally, which means they're encoded as ones and zeros. Let's learn the basics of how this works. Sound is caused when things vibrate, like a plucked guitar string. The string's vibrations cause pressure changes in the air, which creates a wave. Our ears are sensitive to these waves, and they send information about them to our brain, which interprets them as sound. Sound waves are smooth, continuous curves. Analog recording methods, like cassette tapes and vinyl records, record the smooth curve directly onto the recording media. Modern computers don't have a way to store the analog signal directly. Instead, they convert the sound wave into digital code using binary. To do this, they divide the continuous sound wave into discrete segments called samples, then use a binary number to store information about each sample. This sample has a height of 90, so it would be stored as the binary number for 90, which is 01, 011, 010. One of the determiners of sound quality is bit depth, or how many bits are used to encode each sample. Early computers used 8 bits, or 1 byte, to represent each sample. That means each sample had only 256 possible values. Today, most computers use 16-bit audio, which means each sample can be one of 65,000 different values. This audio has a depth of 4 bits. This audio has a depth of 16 bits. Hear the difference? Another setting that will influence sound quality is the sampling rate, or how many samples are taken each second. This rate is expressed in hertz. A sampling rate of 1,000 samples per second is 1,000 hertz or 1 kilohertz. Higher sampling rates have better quality but require more storage space. This audio was recorded at 2 kHz or 2,000 samples per second. This audio was recorded at 44.1 kHz. The drawback to high bit depth and sampling rates is file size. With more samples per second and more bits per sample, high-fidelity audio files can be very large. Every video you've ever seen, including this one, is really a bunch of still images shown in fast sequence. Because our brains aren't fast enough to process each individual picture, we experience the illusion of movement, even though nothing is actually moving. For digital videos, the quality of the video is largely determined by frame rate, resolution, and color depth. Keep in mind that, just like with audio, better quality leads to larger file sizes. Frame rate is the measure of how many images or frames are shown each second. The video on the right is playing at 30 frames per second. The video on the left is playing at 6 frames per second. With higher frame rates, video appears smoother and more fluid. Resolution is determined by how many pixels are in each individual image. Digital images are made of tiny dots of color called pixels. Up close, they look like colored squares, but at a distance, they trick our brains into perceiving a cohesive image. Resolution is measured by counting how many pixels wide and tall each frame is. The more pixels there are, the higher the resolution and the sharper the image. Here's an example of the same video playing at 2 different resolutions. As you can see, the high-resolution video has a clean, sharp image, but the low resolution is pixelated, meaning you can see the individual pixels. Color depth is a measure of how much memory the computer uses to display colors. 8-bit color images use 1 byte of data for each pixel, which means each pixel must be one of these 256 colors. 24-bit color, which uses 3 bytes for each pixel, can use millions of different colors. Again, compare these 2 videos. The better the color depth, the more realistic the video appears. Okay, we've learned about... Hang on, I forgot to change my settings back just a minute. Okay, much better. We've just learned about digital audio and video. Digital audio is created by dividing each wave into samples, then recording the value of each sample. Digital videos show lots of digital images in quick succession. We also learned about factors that contribute to audio and video quality. For audio, we discussed bit depth and sampling rate. For video, we looked at frame rate, resolution, and color depth. One of the most amazing developments in computer technology is the ability to create and display high-quality images. Before computers, photographers shot pictures onto film, which had to be developed in a laboratory before the pictures could be printed on paper. Now, anyone with a smartphone can take a photograph and instantly share it with someone on the other side of the planet. In this video, we're going to look at how computers display images and talk about the 2 types of digital graphics, raster and vector. From a distance, this may look like a white screen, but if you look at it with a magnifying glass, you'll see that it's made up of tiny red, green, and blue lights. This is called an RGB display. Red, green, and blue are the 3 primary colors of light, and they can be combined to make all the colors of the visible spectrum. Each set of 3 lights is called a pixel. Let's use these 3 lights to represent a single pixel. When all 3 lights shine at the same time, our eyes perceive them together as white light. By combining 2 colors, you get the secondary colors of light. Red and green make yellow, red and blue make magenta, and green and blue make cyan. By varying the brightness of one or more of these lights, each pixel can display any color on the visible spectrum. Now that we've seen how computers display images, let's look at 2 ways computers can store images, raster and vector. Raster, or bitmap images, are the most common. Computers store raster images by remembering the color of each pixel. For example, a yellow pixel might take 3 bytes to encode, 1 each for red, green, and blue. Since yellow is a combination of red and green, the computer might store the yellow pixel by using 8 ones for red, 8 ones for green, and 8 zeros for blue. When the computer interprets this data, it turns the red and green lights all the way on and the blue light all the way off. Raster images have several advantages. Because they store each individual pixel, they can be very detailed. Digital photographs, for example, are raster images. Raster files are also easy to create. If you have a camera on your phone, you can create a raster image in just a few seconds. All that detail comes at a cost, though, because raster images use tons of storage space. They also have limits to how much you can scale the file. If you take a small raster image and make it larger, it'll become pixelated, which means you can see the individual pixels. Vector graphics are the other kind of digital image. If you've ever seen a 3D computer animated movie or a video game, then you've seen vector graphics at work. Fonts are also vectors. Instead of storing each individual pixel, the computer stores points and curves. For example, to create a circle, a vector image may store those 4 points, then tell the computer to connect the points with quarter arcs and fill the shape with a color. One of the main advantages of vector images is that they're scalable. That means you can increase and decrease the size of the image without losing any image quality. Vectors are often used to create logos because the same file can be shrunk to fit on a business card and stretched to fit on a billboard. Another advantage is that vector files generally take up less storage space than raster files. That said, vector images also have some disadvantages. For one, they're difficult to create. Anyone with a camera can take raster photographs, but vectors require special software and training. Also, vector graphics usually lack the fine detail of raster images, which is why they're usually used for images with only a few colors. In this video, we learned how computer displays use tiny red, green, and blue lights to create colors. We also learned about raster and vector images. Raster images store the color value of each individual pixel and are great for photorealistic detail. Vector images are infinitely scalable and are useful for fonts and logos.
We create and transmit more files today than we have at any point in our history. Video cameras used to be bulky and expensive, but today most people carry one with them everywhere they go. Anyone who has a smartphone can create picture, video, and audio files and transmit them over the internet. These files take up storage space, which is limited and expensive. Fortunately, we can compress files to make them smaller. Compression is re-encoding a file in a way that uses fewer bits than the original, but it keeps most or all of the information intact. Since smaller files take less space and transmit more quickly, this is a huge advantage. Let's look at a few examples of how compression works. This is a 12-pixel image of the German flag. It has a resolution of 4 by 3 pixels. The color of each pixel is determined by 3 color values, red, green, and blue. Each color value is encoded using 1 byte of data, which means each pixel takes 3 bytes to store. So, this image file will consume 36 bytes of storage space. Let's see how we can use compression to store this file more efficiently. One way to compress data is called run-length encoding. This algorithm takes advantage of the fact that many images use the same pixel color multiple times in a row. For example, the image starts with 4 black pixels. Instead of storing each individual pixel, the computer could store the number 4, then the 3 bytes for the color black. The red and yellow pixels could be stored the same way. The number of pixels, then the color value. Using this algorithm, this image would consume only 12 bytes of storage space, 1/3 of the original. Algorithms like run-length encoding are called lossless compression techniques because they don't lose any information. The decompressed file is identical bit for bit to the original uncompressed file. GIFs, PNGs, PDFs, and zip files all use lossless compression. There are other compression techniques that change the original file a little bit. These techniques are called lossy compression and are most commonly used for image, video, and audio files. Lossy compression takes advantage of the fact that human sight and hearing are imperfect and can't detect small losses in the data. Here's an uncompressed photograph. Let's zoom in to the top left corner so we can see the individual pixels. As you can see, each pixel is a little bit different from the others, so using run-length encoding wouldn't work well here. However, the computer can change the pixels just a little bit to make them more similar. Here's the same square of pixels after compression. Now the computer can store this file using much less space. Of course, if the computer simplifies an image too much, there will be a noticeable drop in quality. However, by making small adjustments, the file size can drop significantly without any visible differences. The picture on the left is a 12 megabyte file, and the image on the right is 2 megabytes. For images, the most common lossy file type is the JPEG. Videos, as you know, are really just rapid sequences of still images called frames. This means they can use the same compression techniques we've just looked at. However, they can take things a step further, because most videos have some pixels that stay the same from frame to frame. For example, this background doesn't change at all between frames. This is called temporal redundancy. Instead of retransmitting these pixels for each individual frame, the compression algorithm copies them forward. Without this kind of compression, it would be nearly impossible to stream videos over the internet, since it would take too long to transmit all of the information. Of course, if the video is heavily compressed, the computer may retransmit patches of data that should have been changed, which can cause funny-looking areas called compression artifacts. If you're watching a movie or TV show, compression artifacts can get in the way of the experience. However, many instructional videos, including the ones in this course, are heavily compressed and have a few artifacts. This is to make the video files as small as possible, which makes them watchable even on slow internet connections. The most common file type for compressed videos is the MP4. Just like image compression, audio compression takes advantage of the limitations of human hearing. For example, our ears are very sensitive to sound frequencies in the vocal range, such as talking and singing. However, some frequencies are much too high for us to hear. Most audio compression techniques discard data in the ultrasonic range, since we can't hear it anyway, but preserve data in the vocal range. Some compression techniques go even further and compress even the vocal range. This is why voices sound different when you talk on the phone. The audio is compressed so more people can use the telephone service at the same time. The most common file type for compressed audio is the MP3. MP3s are as much as 10 times smaller than uncompressed audio files.
The word hardware refers to the physical components of a computer. The main functions of computer hardware are input, output, processing, and storage. In this video, we'll focus on input and output hardware associated with desktop computer systems. These are commonly referred to as peripheral devices. Peripheral devices are used to expand or customize the functionality of a computing device. They usually connect to your computer through an external port or through a wireless connection. Even after the system has been set up, you can still add or remove peripheral devices as necessary. Input devices allow you to send data or commands to the computer. There are several types of input devices. The first one is a keyboard. A keyboard allows you to send alphanumeric information to the system by pressing keys. When you press a key, the corresponding character is sent to the computer hardware. The software running on the system then does whatever it has been programmed to do with that keystroke. External keyboards are required for desktop systems, but are optional for laptop and mobile devices, which use integrated keyboards or on-screen keyboards. For desktop and laptop systems, keyboards typically connect using a USB port, but they can also be connected wirelessly. External keyboards can be connected to mobile devices as well using a wireless connection. Another type of input device is the mouse. The hardware within the mouse is able to keep track of its physical location on a hard surface. Using this information, it can determine how far you have moved the mouse and in what direction. This information is sent to the computer, which moves the cursor on the screen accordingly. An external mouse can be connected to a desktop or laptop using a USB port or a wireless connection. A related type of input device is the touchscreen, which is commonly used by mobile devices. A touchscreen uses a special material overlaid on the top of the device's regular screen that can detect when you have touched it and where. As with a mouse, touchscreens can be used to send data and commands to the device. Scanners can be connected to a computer to allow you to scan paper documents into digital files. Scanners can be connected to desktops or laptops using a USB or FireWire connection. Wireless scanners are also available. Digital cameras and webcams can be connected to computers to input digital images and video into the system. These devices are commonly connected to desktops and laptops using a USB, FireWire, or wireless connection. Mobile devices already include integrated cameras, so they are not commonly used with external digital cameras and webcams. To record audio, a microphone can be connected to a desktop system using a USB connector, an audio jack, or a wireless connection. Laptops and mobile devices already have integrated microphones and are less likely to have an external microphone attached. Computers use output devices to display or send information. The most common type of output device is the monitor. Information is usually displayed on a monitor screen as it's being processed by the computer. Laptop and mobile devices use an integrated screen, while most desktop systems use an external monitor connected to a video port. Another type of output is audio. Modern computing devices can send audio output to a set of speakers, which may be integrated into the device itself or plugged into an external connector. On a desktop system, speakers can be connected using a USB cable, an audio jack, or a wireless connection. Frequently, we need to create a hard copy of the information processed by the computer. This is done using a printer. Data is sent through a wire or over radio waves to a printer. The printer receives the data, formats it, and transfers it onto a piece of paper. Printers are commonly connected using a USB port, a FireWire port, or a network connection. In this video, we introduce computer peripherals and how they connect to a computer system. Input devices allow us to send data and commands to the computer. Output devices display and transmit information that has been processed by the computer.
Computers use a variety of interfaces to connect external devices. In this video, we'll learn about some of the most common types of ports, connectors, and wireless methods for connecting devices. The most commonly used type of connector is the Universal Serial Bus, or USB connector. USB allows you to connect a variety of external devices, including printers, digital cameras, external hard drives, and smartphones. USB ports and connectors come in four shapes. Type A connectors are rectangular in shape. They are designed for connections that may be plugged and unplugged frequently. Type B connectors are more squared in shape, with a bevel on one edge to keep them from being plugged in backwards. They are designed to be used for connections that are left plugged in for long periods of time. Mini USB connectors are a smaller type of USB connector. They are commonly used for devices such as digital cameras. Micro USB connectors are even smaller still. They are commonly used for connections to mobile devices such as tablets and phones. Most computer systems have 2 to 6 USB ports, allowing you to connect that many devices to the system. If you need to connect additional devices, you can expand the system by connecting a USB hub to one of these ports. A USB hub allows you to connect additional USB devices through just one port on the computer. Some computers provide a FireWire connector. It looks a lot like a USB connector, but it's beveled on one end to keep you from inserting the cable incorrectly. FireWire functions in much the same manner as USB, allowing you to connect external devices such as digital cameras, extra hard drives, and scanners to the computer system. Most computers also provide audio connectors like these. The blue one is the line-in connector, which can be used to connect an external audio source to the computer. The green one is the line-out connector, which is used to connect speakers to the system. The pink one is the microphone jack, which is used to connect a microphone to the system. Computers also provide video connectors, which are used to connect an external monitor to the system. The following types of video connectors are commonly used. The Video Graphics Array, or VGA connector, is used to connect older monitors to the system. You can identify this connector by its blue color and the 3 rows of 5 pins. The Digital Visual Interface, or DVI connector, is typically white with 3 rows of 8 pins. DVI has been superseded by the High Definition Multimedia Interface, or HDMI connector, which is used to connect the system to an HDMI monitor or TV. Like HDMI, the DisplayPort and Mini DisplayPort interfaces are used to send high-quality digital video and audio signals. The main difference is that the HDMI is beveled on 2 corners and DisplayPort is only beveled on 1. The Thunderbolt interface is compatible with DisplayPort and is primarily used on Apple computers. Thunderbolt ports can also provide DC power. They are mainly used for external displays, but they can also be used to connect other peripheral devices. Most computers provide a connector that allows you to connect the system to a network. This network connector is called a registered jack 45 or RJ45 jack. To connect the system to a network, plug a network cable into this connector. Computers can also connect to external devices using wireless communication. Infrared or IR communication technology uses light waves to transmit information through the air. The light used by IR devices is just past the visible red light spectrum, so it's invisible to us. The simplest example of an IR device is a TV remote. When you press a button on a TV remote, IR light is emitted from the front of the remote and picked up by an IR receiver on the TV. Infrared is used by some portable devices such as tablets and smartphones. However, because of its line of sight and distance limitations, most devices use Bluetooth to communicate wirelessly. Bluetooth is a short-range wireless communication technology used by many devices. It uses radio waves that operate between 2.4 and 2.485 gigahertz. Most Bluetooth devices have a range of about 30 feet. The nice thing about Bluetooth is that it's able to operate without a direct line of sight between devices. There can even be some obstructions between devices, such as thin walls. This versatility has made Bluetooth the short-range communication method of choice for devices like wireless headphones, speakers, keyboards, mice, smartwatches, printers, and game controllers. In this lesson, you learned about common computer ports and connectors. USB and FireWire connectors are used to connect external devices to the system. Audio connectors are used to connect speakers and microphones to the system. Video connectors are used to connect monitors.
Installing external devices on a PC or a laptop is usually straightforward. You plug the device into an open port and then wait a few seconds for the computer's operating system to recognize the device and install the software needed to communicate with it. The term plug and play applies to these easy installations. Sometimes, however, installing external devices can be a bit more complicated. And this video will provide installation tips for common scenarios. USB devices are hot swappable. This means you can plug and unplug USB peripherals while the system is running. The system will automatically detect the addition or removal of a device and make the necessary configuration changes. Before disconnecting external storage devices, you need to stop them properly before removing them to prevent data corruption. USB devices can be plugged in directly to a USB port on the computer or to an external USB hub that's connected to the computer. USB ports can provide power over the connection. USB devices can receive up to 500 milliamps of power from a USB 2.0 port and up to 900 milliamps of power from a USB 3.0 port. If a device can operate on this much power, it's considered a bus-powered device, which means the USB port provides 100% of its power. If a device needs more power than this, then it's considered a self-powered device and will typically have an external power adapter that plugs into a wall outlet. For some peripheral devices, you may need to load drivers before connecting the device for the first time. Drivers contain software instructions that the computer needs in order to communicate with the device. For many devices, the necessary drivers are included with the operating system. Other devices may require you to manually install the drivers on the system prior to the first connection. Device drivers may also need to be updated when manufacturers fix bugs and vulnerabilities. If your computer has access to a local network, either wired or wireless, you might install and configure peripherals to be accessed over the network. For example, you might install an Internet Protocol or IP-based printer and then configure it using a web page in a browser. Another example would be a Wi-Fi access point. If you install an external device and it's not functioning correctly, consider the following troubleshooting tips. Check all cables and connectors to make sure they're securely seated. If the device requires a separate power source in order to operate, verify that it's plugged in. If you're installing the device on Windows, open Device Manager and make sure the device is listed and enabled. Try installing the device on another computer system to make sure the problem doesn't lie with the device itself. Update the device driver. If you've recently updated the device driver and the device no longer works, roll back the driver to the previous version or revert the operating system to an earlier restore point. In this video, we talked about installing external devices to a computer system. We discussed plug-and-play installations, updating device drivers, working with IP-based peripherals, and configuring a web-based installation.